Alright, welcome to another video. This one's going to be about cracking. So, this is going to be kind of hard to read, so I'm going to type up as well. But the video is pretty much going to be about what cracking is, why we do cracking, the different types of cracking. It's usually a very short part of it. Very rarely comes up, but you just need to know what it is and why you do it, and you'll be fine. So what actually is cracking? Cracking is the process of converting very long chain hydrocarbons into a high percentage of short chain useful alkenes. Yeah, alkenes and alkanes and alkenes to meet demand. Alright, so let's take this example here. So this is undecane. It's an 11 carbon long compound. The problem with this is that in industry you don't really want to use this that often. It's too long. It's not going to get used that often because you want to use it for example, in fuel you want it to be flammable. This is not very flammable. The longer your carbon chain, the less flammable it is because it's going to form more van der Waals forces, and on top of that, it's got very strong carbon-carbon covalent bonds. You have to break those carbon-carbon covalent bonds as well. So a lot of energy is needed to break this compound down and to make it flammable. So you're not going to use it very often. There's very low demand for this, but there's a very high demand for gasoline, or an alkene that could be used for a polymer. But anyway, so here's the example here. I you don't usually draw it like this, but yeah. So I just wanted to get I drew out the displayed formula for this part here because that's the part that's going to be broken down. So, this bond here. Anyway. Yeah, so I forgot to mention, you want to get an alkene. When you break it down, you get an alkane and an alkene. I'm going to explain why you get an alkane and an alkene. Your alkane is going to be a short chain, for example, a 5 carbon long compound like pentane. That's more flammable, and you're going to get an alkene. I'll show you how. So you don't need to know this, but just for you to understand why it's happening. So you get it's probably a bit too close, but that is a terrible cloud. There we go. And then you have so that gets split here. I put R1 and R2 because I'm not going to write the rest of it. It's all good, and that doesn't change. But this part here, that does change. So these can just, react together again, but that's, you're going to get exactly what you started off with. So that's not going to get you the reaction you want. You want to split them up again. The whole point of this is to split them up. So here, because this positive charge here is going to get attracted to this, the electron here is going to get attracted to form a double bond here. So bond's actually going to go no. Alright, so this is here. So from there to that bond, this gets separated away. So then you have R1, CH2, see. Because this H plus will get removed now because the electron here is going to this one here, releasing a H plus. Now that's now formed a double bond here. So just separate them out. Remember the H plus is gone now. Now you have four bonds total here, and then you've got 1, 2, 3, and then your 4 here, and then that bond here, obviously, between this one here. Yeah, CH3, that's your alkane, and then this would be your alkene. I know it's terrible drawing there, but you don't really need to know all of this. But it's the point of understanding that you're gonna get an alkane and an alkene. Why is this possible? Now this alkane here, I can tell you for a fact that's gonna be 1, 2. Oh, I'm gonna say 1, 2, 3, 4, 5, 6. Hexane. Hexane, yeah, can be used as a fuel for cars. I think you can use hexane. Yeah, you can use hexane for fuel for cars. And obviously that's you're gonna need fuel. A lot of cars need fuel. A lot of cars are being used all the time, so that's going to be in high demand compared to this, which is inflammable. This is much more flammable and in demand. But alkenes, you can use them because they have the double bond. You can use them for other reactions, for polymerization. So that's why they're very useful. So plastics, clothing, you're going to need these polymers here. So that's why these are in very high demand as well. Yeah. One way to actually prove that you have your compound that your compound has been cracked is because you have the alkene here. Alkenes actually undergo bromine water. They decolorize bromine water, obviously. So you'll separate your compounds here usually by distillation, because they should have different boiling points. This should have a lower boiling point because that double bond kinks the structure a little bit more, and it can't form as much. It can't form as many van der Waals forces. So when you separate them out, get one compound here, one compound here. If one decolorizes water, if one decolorizes bromine water and the other one doesn't decolorize bromine water, you have at least one. You have one alkane and one alkene, which means that cracking has occurred. So your reaction is finished. Make sure that you say the reaction goes from orange, or the bromine water is going from orange to colorless, not clear. Clear won't get you the mark. Like, even though it looks clear, examiners are very stingy. So I guess say colors. All right. So there's two forms of cracking that you need to know. One is thermal cracking. Thermal cracking has harsh conditions. It uses quite a lot of energy. So it has temperatures i.e. temperatures 1000 degrees Celsius. There you go. Which is approximately 1273 Kelvin. So that's already a lot of energy. And 70 atmospheres of pressure. So, and that breaks it down into, or cracks your compound into a high percentage of alkenes and comparatively fewer alkanes. So yeah, so now I've said this, so if you want to produce a lot of alkenes, this is a very good reaction to do. So much weigh up the positives from this. I'm not gonna write them down because I'm not bothered. I don't care. But when you get these types of questions, they usually ask you for the benefits. You'll get those like 5 mark questions, like maybe of why you may choose to do this reaction over the other reaction, which is catalytic cracking. Advantages in this case would be you're producing a high yield of alkenes and low yield of alkanes. So you may, if you want to favor it to get alkenes, that's still good. And even if you want to get alkenes, you're still getting quite a few alkenes, which is also very good. However, obviously the disadvantage is that 1,000 degrees Celsius for a long period of time is quite expensive energy-wise, and obviously maintaining 70 atmospheres of pressure is also quite a lot of energy. It's also dangerous as well. Like it's quite dangerous to have those temperatures. You have to make sure you have the equipment to make sure that whoever's using it is still safe. Because health and safety is also something that you could talk about in those questions. I'm trying to think if there's anything else. I mean, that's probably already like 3 or 4, like half your marks already. We haven't talked about catalytic cracking yet, so that's already half your mark. So, yeah, I'm just gonna go with that for now. So then there's that's not working. There you go. Great. All right. So then there's catalytic cracking. Catalytic cracking, it has it in the name. It uses a catalyst. And catalysts usually lower the activation energy by providing they provide a new pathway for the reaction to happen with a lower activation energy. So obviously it lowers the temperature. And pressure. And obviously because you don't have it's lower activation energy, you don't actually need to have as high a pressure as well. So as a result, less energy used. That's going to lead to reduced costs. And reduce costs in the higher rate of reaction. So the conditions for this reaction are so 450 degrees Celsius, which is much lower than 1,000 degrees Celsius. Only it only needs to be just above atmospheric pressure. So yeah, above. And then in cracking, we call these, or in cracking. So yeah, in cracking, we call the catalyst zeolites. So catalysts, AQA zeolites. They have their own special name for this type of cracking. Like this type of catalyst is usually containing aluminium or silicon and oxygen. So usually one of those has those compounds in it. So alright, and products of the cracking, the cracked products are benzene. So they usually are benzene rings and short hydrocarbons. So if you're weighing this up, so positives from catalytic cracking is that obviously you use lower temperature and lower pressure because of that catalyst that provides an alternative pathway for the reaction to happen under low activation energy, which is good because you need to, as you can see here, lower temperature, much lower pressure, so cost is much lower. This makes it a much more efficient reaction in production. Because they can do this reaction many more times and not use as much, and not cut into the cost too much. However, the things you have to consider as well from this is that your zeolite has to be very specific, obviously. So, and it might poison. You don't do poisoning until year 2. You don't need to know about poisoning of catalyst, but you could risk ruining your catalyst. That's one thing. But more importantly, your products, you're getting a benzene ring and short hydrocarbons. You don't want benzene, unless you really want a benzene ring. You want to get your alkanes. You don't want to get a benzene ring. In practice, you have to break down the benzene ring again, and benzene rings are very difficult to break down. They're quite strong as well. So that's a whole new process of breaking it down as well. You have to have a full plan to breaking that down, and only a very small yield of hydrocarbons. So that's a massive problem for what you're trying to get, and that's highly dependent on the catalyst that you use. But catalysts are very specific, so it's very hard to get a catalyst that will actually break it down into compounds that you want. A small thing you could say benzene rings are carcinogenic, but you don't need to talk about it being carcinogenic. You're usually very careful about those things. But if I was to compare the two, it depends on what you're looking for. If you want to get a high yield of alkanes or alkenes and alkenes and alkanes, you're gonna have to take the risk or sacrifice your energy bills. But at the same time, if you want to get save on costs but get a short number of hydrocarbons, you can use catalytic cracking. But obviously you're not going to get as high yield. So yeah, that's it.